This is AP Calculus AB, Notes 1.5, Limits of Trig Functions. Trig is the best. You know it. I know it. We all know it. We've already looked at how to evaluate limits of trig functions by direct substitution, provided the function is defined and continuous at theta. Let's find this limit. So just a little recap. This is going to be the limit of theta as it approaches pi. Now we could rewrite this quite a bit if we wanted. We could put the 2 out in front. We could say this is cosine of theta, and then once we find the limit, we're going to square it. You wouldn't have to write all that. I just did. So this is going to be 2 times cosine of pi squared. Now cosine of pi is -1. -1 squared is 1, so this is just 2. Quick reminder how I know that cosine of pi is -1. In a coordinate plane, pi is on the negative x-axis. Anytime we want to know what a trig function is at a certain point in the coordinate plane, we have to know what x, y, and r are. Y is obviously 0. We didn't go up or down. X can be any negative number that you choose, but r has to be that same number, but it has to be positive because r is always positive. Cosine is x over r. It's -1 over 1, which makes it -1. That's why this was -1. Not all functions are undefined at a value, but their limits do exist. The same is true in the trig world. That is an awkward sentence. Not all functions are undefined at a value, but the limits exist. Yeah. Evaluating trig limits by rewriting the function using identities. So if we were to try to evaluate this right now, here's what would happen. If we try to use direct substitution. If you put 0 in here for theta, sine of 0, that's on the positive x-axis. That's y over r, that's 0 over 1, that's 0. That makes this undefined because we're dividing by 0. So we're going to have to manipulate this using trig identities that you learned without me because of the old COVID. Hopefully you recognize that sine squared of theta we could replace with 1 minus cosine squared of theta. Quick review why. Sine squared of theta plus cosine squared of theta is 1. That is the first trig identity that you learned. Then if you subtract cosine squared of theta from both sides, you get sine squared of theta equals 1 minus cosine squared of theta. If you know this without doing the work, then don't do the work. I'm just showing you as a reminder of those who may not remember. So this is going to equal the limit as theta equals 0, as theta approaches 0. The numerator, there's not much we can do with. This denominator, this is the difference of 2 squares. One's a perfect square, cosine's a perfect square. When you factor the difference of 2 squares, it's 2 binomials. You take the square root of each term and you make one. Let me stop for a second. Square root of 1 is 1. That goes in the first position of the binomial. Square root of cosine squared goes in the second position. And you do the same for the second one. You make one of these plus, one minus. It doesn't matter which is which. These cancel, leaving us with a 1 in the numerator. So now we have the limit as theta approaches 0 of 1 over 1 plus cosine of theta. We can use substitution now to figure this out. If we replace theta with 0, cosine of 0 is 1. So this becomes 1/2. Once again, the reason I know cosine of 0 is 1, 0 is on the positive x-axis, and there x, y, and r, x is 1, r is 1, 1 divided by 1 is 1. Number 2. Let's see, if we were to try to use substitution directly for this, horrifying things would happen. Tangent of 3 pi over 2, that is 0. 3 pi over 2 is on the negative x-axis, negative y-axis, I should say. I'm just going to draw this just to remind you. In this location, y could be -1, x could be 0, r could be 1. Tangents y over x, that would be undefined. So let's try to manipulate this using trig identities. This argument really should be in parentheses. So it's the limit as theta approaches 3 pi over 2. Tangent is the same as sine of theta over cosine of theta. That's super helpful because these cosines cancel. And since they cancel, I now have the limit as theta approaches 3 pi over 2 of 3 times sine of theta, which is the limit as theta. Actually, I don't need to write limit anymore. I can just evaluate it. I'm going to evaluate the limit by putting 3 pi over 2 in for theta. So that's 3 times sine of 3 pi over 2. Sine is y over r. That's going to make this -1. 3 times -1 is -1. So this limit is -1. We couldn't use direct substitution because there was a hole in the graph. We canceled out the cosines. And the same thing happened on the previous one. We couldn't use direct substitution because there was a hole in the graph. Number 3. Hey, we can use direct substitution for this, can't we? Yeah, no, we can't. Pi over 2. Secant of pi over 2 is undefined. But here's what we can do. Secant and cosine are reciprocals. If you multiply two reciprocals, you get 1. Well, that's easy. It makes this 1 over 4 times theta. So if we substitute using direct substitution for this limit and put pi over 2 in for theta, this is going to give us 1 over 2 pi, because we could cross cancel here. 2 goes into itself once, and it goes into 4 2 times. Number 4, let's see. Sine of theta is 0. We'd be dividing by 0 if we left it like this, so we cannot do that. So we're going to have to manipulate this, and I encourage you, if you're watching this at home, where else would you be watching it, to stop the video and try this on your own. It's likely you're going to learn nothing from just watching me do it. You need to try it on your own and then struggle. I'm going to change everything in terms of sine and cosine. Tangent is sine over cosine. So I can cancel those cosines. Now I have the limit as theta approaches pi of sine of theta over sine of theta. Sine of theta is cancel. Now we have the limit. Now when I say cancel, in this context, you're dividing something by itself. It means you're left with 1. What's the limit of 1 as theta approaches pi? Well, it's 1. Just a reminder, this is a horizontal line that's 1. Doesn't matter what x value you pick, the y value is always going to be 1. Now there are some arguments to not teach you this next part. Now, what you currently know about limits, this would be important to know. By the time we get to the end of this course and we learn L'Hopital's rule, it makes memorizing these special trig limits obsolete. But once again, we can't learn those special trig rules for a long time. So we're going to learn this now, these special trig limits. So here we go. Notice in each case, x is approaching 0 for all 4 of these. So this first one is kind of like 1. If you have sine of an angle, and that's being divided by the same angle, and x is approaching 0, then this limit's going to always equal to 1. And if this is reciprocated, it's the same result. If you have an angle divided by sine of that angle, and x is approaching 0, then this limit's going to always be 1. I can prove this to you, and maybe I'll take the time to do that sometime, make a special video over that. This one down here, if you have cosine of an angle, and then you're subtracting one outside the angle, and that's divided by the angle, that limit's going to be 0. And if you interchange and it's 1 minus cosine of an angle over that angle, then that limit's going to be 0 as well. So you should memorize these. So far, we have very little memorizing here. We have the limit existence theorem, and we have this, and I believe that's all that you need to memorize at this point. So let's see if we can apply this. Find each of the following limits. Well, we can find this by direct substitution. E to the 0 times cosine of 0 over 4. Anything to the 0 power is 1. Cosine of 0, also 1. So this is just 1/4. We didn't have to do anything special with this. All right, number 2. We can't use direct substitution because if we try to do that, we're going to end up with 0 here on the bottom. I'm just going to bring this down here so we can see what we're trying to accomplish. If we can manipulate this equation so that we have sine of an angle over the same angle, we know this limit's going to be 1. But you notice sine of the angle's 4 theta. You can't do anything with this angle. That cannot change. But it's not being divided by the same angle. So how can we fix that? Well, let me tell you how we can fix this. You are allowed to multiply by 1 anytime you want. If I multiply this by 1, it will not change the value, but it could change the way it looks. I'm going to multiply by 1 in the form of 4 over 4. I'm going to put this 4 here strategically so that these are identical. Then I'm going to take this 4. I could put it here, or I could just pull it all the way out to the front. If I did that, now, using this right here, this limit is supposed to be equal to 1. And then we had that 4 out in front. 4 times 1 is 4. Long story short, you can manipulate things by multiplying. If you do it to the top, you got to do it to the bottom as well, vice versa. But you cannot manipulate the angle. You can't change it. All right, number 2, or number 3. We would like for this angle, 2x, to be the same as this, 3x. It clearly isn't. To make this easier for my brain, I'm going to pull this 3 out to the front. Now, to be clear, this 3 is not a 3. It's a 1/3. The 3's on the bottom. So if I pull the 1/3 out to the front, I could write this as the limit as x approaches 0 of sine of 2x over x. Now to fix this so that this is the same angle as this, I'm going to multiply by 2 over 2. 2 over 2 is 1, so I haven't changed the value. These are now the same. This is approaching 1 according to our special trig limits above. So I have 2/3 times 1, which is 2/3. See if we're getting better at this. Try this one on your own, please, and then come back and watch the video. And we're back. 2 and 3 we can pull out to the front as a 2/3. You cannot manipulate the angle. So if I want a 5 to be down here on the bottom, I could have put a 5 up here on top. You could put the 5 here, or you could put it out here. This is going to be 2/3 times 5, and then this limit here is 1. That's going to make this 10/3. Number 5, trying direct substitution will be useless because if you put 0 in for theta, you're going to be dividing by 0. But we could manipulate this. I'm going to rewrite this. You'll see why here in a second, I think. I'm going to rewrite this as tangent of theta times 1 over theta. And then tangent I'm going to write as sine of theta over cosine of theta. Now this doesn't look helpful at all. But if I rewrite this so that this theta is underneath the sine and this cosine's over here with a 1, then it actually becomes helpful. Life is all about perspective. So is trigonometry. Now this limit we can evaluate. According to our special trig limits, that's equal to 1. And then cosine of 0 is also 1. So that makes this answer simply 1. Number 6, once again, I encourage you to try this on your own first. I want to try, I don't know what to do. So when in doubt, do something. If you don't know what to do, do something. The only thing that is apparent to me to do is to factor a 2 out of this. How will that help? I don't know. And now I know how it helps. I can change 1 minus cosine squared of theta to sine squared of theta. I'm also going to pull this 2 out to the front here. Using a trig identity, that becomes sine squared of theta. And then I want to use these special rules that I just learned, so I don't have this theta on the bottom. So to do that, I'm going to separate this sine squared into a sine of theta and a sine of theta. Here's how that helps. Using our special trig rules that we learned, this becomes 1. To evaluate this limit, we're going to put the 0 in for theta. So that's 2 times 1 times sine of 0. Sine of 0 is 0, so this is just 0. All right, we got 3 more. We haven't used that special cosine rule yet, have we? It's too bad. Number 7, let's try to use that special cosine rule that I just mentioned. So let me just get a picture of that and bring it over so we can see what we are trying to compare this to. That did not work. Copy. Paste. There we go. This is for reference once again. What? Did I just do that? Oh, okay, grabbing the wrong thing. Is that what's going on? Copy. Making a fool of myself. There we go, there we go. Sloppy Joe. If you're wondering what it sounds like when someone's lost their mind, I believe you've just heard it. All right, we would like to try to use this. Please note, we can't use direct substitution for this because we'd be dividing by 0. 1 minus cosine of an angle over the angle, we kind of have that here, but this thing is hanging around. We don't really want that hanging around. So what we can do is we can separate this and make this the limit as theta approaches 0. And we could write this as 1 minus cosine of theta over theta. And then we could add to that the limit as theta approaches 0 of sine of 2 theta over theta. We've just taken this fraction and separated it into two separate fractions. That's all we've done. Now this here, according to this, should be equal to 0. Same angle on top and bottom, and it's 1 minus cosine. So that's done. And then over yonder, we could do something similar if this was the same angle, and it isn't. So I can make it the same angle as long as I also put a 2 in here. And let me put that 2 someplace better. Let me put it out here. So now this limit is 1, and we're multiplying it by 2. So it's 2 times 1. 0 plus 2 times 1, drop in a deuce. Number 8, let's try something similar with this. Let's see. So I got ideas, I just don't know if they're any good. I'm going to separate my fraction like I did on the last one. I'm just going to write limit once this time. Last time I wrote it twice. What's the advantage of writing it once or twice? Well, it's just whichever makes the most sense to you. Nothing inherently better about writing it once or twice. Whoops, I left off a theta here. So it would look like this if we separate our fractions. And then here we're dividing something by itself. So that cancels. That means this is the limit as theta approaches 0 of 1 plus. And over here, the reciprocal of cosecant is sine. So since cosecant's on the bottom, I could replace this with sine and put it on the top. That does not change this theta. It's nothing to do with it. And then what do we got? Well, according to our rule here, this is going to equal 1, special trig limits. So this is going to end up being 1 plus 1. It's a little something I like to call 2. Number 9. Direct substitution is going to result in this x squared being 0 squared, which is 0. So I can see that I can factor for this. Is it going to be helpful? Don't know. Let's try it and see what happens. The numerator, both terms have a factor of sine of x. Then this is, the numerator has a product, and so does the denominator. I'm going to separate those products. So it's two separate fractions I'm multiplying together. Sine of x over x times 1 minus cosine of x over x. The reason that I chose to separate it in that manner is because this is a special trig limit, and this is a special trig limit. This one, as x approaches 0, is approaching 1. This one, as x approaches 0, is approaching 0. So this is 1 times 0, which is 0. All right, please do 1.5